Okay, welcome to lesson 48. We're going to solve some polynomial equations. This is a sort of a, what do you call it, a culminating lesson or something. We've been playing around with our polynomials, factoring polynomials in lesson 47. We learned a little bit about, complex numbers in the last lesson. And now we're going to put all that information together, all the information from the beginning of the term really. We're going to put it all together to actually solve some equations. Now notice this byline here. It says, including cases of complex solutions. That's why we were looking at complex numbers. Often you're going to see instructions that say something like, solve in the complex number system. And when they say solve in the complex number system, what they're saying is, use the complex numbers. When you're writing your solutions, let yourself use complex numbers. In other words, find all the solutions, the real ones, and if there's complex ones, they involve the I, remember complex numbers or things like this. If you have complex solutions, you should list those too. All the solutions, all of them, not just real solutions. You get a square root of negative, we don't have to stop. We know how to keep going, right? We learned that last time. Anyway, we'll see some complex solutions come up, I promise. So let's get started here. We're going to solve some polynomial equations. Now the workhorse method here is solving by factoring. Factor the polynomials. So that explains why we had to do a lot of factoring, right? And the goal when you're solving by factoring is to get a factored form on the left side of your equation and then a 0 on the right side of your equation. If you have a factored form on the left and a 0 on the right in the book, you will see this called a perfect equation. Perfect equation. It's perfect because you can start to read your solutions right off it. So if you get your equation in perfect form, I guess you would call it, you can start reading your solutions. So I'll show you this in action right here. So you see this polynomial equation. Hey, it equals 0 on the right. Woohoo! Happy about that. It's not factored on the left. Guess we got some work to do, huh? So that's a trinomial. Remember how we did these? The 3x squared. Well, that must have come from somebody multiplying a 3x times an x. I mean, the presumption is we're going to FOIL two binomials here to get that trinomial. So the 3x squared is 3x times an x. Then you have to take the negative 8, and you have to break that up, and you say, well, negative 8, what could I have? I could have a negative 1 times an 8, or I could have a 1 times a negative 8, or I could have a negative 2 times a 4, or I could have a 2 times a negative 4, right? And remember also, you have to try these in both orders, right? So that means I've got what now? I've got 1, 2, 3, 4, doubled basically to 5, 6, 7, 8. I got 8 possible things to try here. 8 combinations of numbers to put in my parentheses and see if they work. So rather than just raw guessing and checking, I think I'm going to try to make a guess here. I'm trying to get a 10, right? So what would happen if I put like a, how about like a 4 and a 2 here? So my idea is that I'll have an outer product of a 12x and hopefully subtract an inner product of a 2x. Now I have to make sure this works. Oftentimes, whether you get a +8 or a -8 kind of messes you up. You think you're onto something, it turns out you're not, but let's see. I need a +10x, so I would want to have a +12x and a -2x. You know what? This is so going to work. There it is. That worked. So just to double check, 3x times x is 3x squared. Yep. I got the +12x. I got the -2x. That gives me the 10x. Yep. And then the negative 2 times the 4 gives me the negative 8. Yep. 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 Yep, yep. It worked. So let me maybe get these out of the way now. Get out of the way. Get out of the way. Okay. So this, I can now say equals 0. So let's just kind of divvy that stuff up. There's my equation in perfect form. It's a perfect equation. It's factored on the left. It equals 0 on the right. Now here's why it's nice to have it factored. New color. Remember, this counts as a single object. When you put things in parentheses, it says that's a thing. 3x minus 2. That's a thing. I got a thing times another thing. And when I multiply these two things, I get 0. Well, how do you get 0 when you multiply two things together? one of the things has to be 0, right? You can't take two things that are not 0. You can't multiply 2 times 3 and get 0. You can't multiply 4 times 5 and get 0. One of them has to be a 0. See, that's the big thing here. So having the 0 on the right means that one of these things has to be 0. So either 3x minus 2 is equal to 0, or x plus 4 equals 0. So again, I guess you see now why it's so nice to have a factored form equals a 0. It enables us to just look at each factor separately and set it equal to 0 separately. So our one equation has actually turned into two equations. We're going to get two solutions here. So this one's easiest to solve. X equals negative 4. Yep. And then this one's not so bad. I mean, let's try to do it all at once because I'm running out of space. You'd have to add the 2 to both sides, right? And then you'd have to divide both sides by 3. Do you see how that worked? If not, you can always just work it out by pencil to make sure. But yeah, it's going to be 2/3. So I could say the solution set is a negative 4 and a 2/3. If you'd like to put it all in a set, you can do that. Cool. That's our general approach to solving polynomial equations. Now there's just details. From here on, it's just seeing more situations. Well, here's another situation. Now I'm looking at this equation. I'm saying, I do have a factored form on the left. Woohoo! Oh, it's not a 0 on the right. Got to fix it. It has to be a factored form on the left, and it has to be a 0 on the right. So I'm going to have to subtract that 6 on both sides. I've got no choice here. So I subtract the 6 on both sides. Okay, now it equals 0, except this is not a factored form. It's a subtraction. It's something minus 6. That's a subtraction. That ain't going to be good. So I'm going to have to rearrange, kind of massage the left side here a little bit. So I'll distribute my x here. 8x squared minus 13x. Okay, and then minus 6 equals 0. Well, okay. Looks like we got another one of these trinomials here, folks. Well, the 8x squared could be an 8x times an x, or it could be a 4x times a 2x. Which is it? We don't know yet. I'm going to come over here and I'm going to play with the 8x times the x first, because when I see big numbers like a 13, I usually suspect that we're going to use the 8 and the 1. And I don't know that for sure. I'm just going to have to try. Now the 6. Well, it could be a 2 and a 3. You know what? I like the 2 and the 3. Why? Remember, we're trying to get a negative 13x here in the middle, right? That's supposed to come from you're combining your outer and your inner products. Note the 8x times the 2 here is going to give me a 16x. The 3 times the x is going to give me a 3x. Now, if I want a minus 13x, what I'm hoping is that I can do it this way. A negative 16x, which would make that a minus 2, and a plus 3x, which would make that a plus 3. And I just have to double check. Double check. Plus 3 times minus 2 is minus 6. Okay, good. It worked. You always have to check that part, because sometimes you get it to work and it's like, oh, signs don't work. It works. So let me erase some of this stuff then. It's pretty cool when you've got enough practice with trinomials. You can kind of get quicker at them. Okay, so that's my factored form. Let's see, can I erase just the green? Hey, not bad. Don't forget, this equals 0, right? This all started as an equation. Blah, 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 blah equals 0. So that stuff equals 0. Cool. So now that I've got this perfect equation, and it's factored on the left, it equals 0 on the right, now I can look at these two sides. Here you can tell just by looking at it, what would you plug in for x to make this a 0? Well, you'd have to plug in a 2, right? If I just do this all out by hand, you take the x minus 2 factor, set it equal to 0. That gives you a possible solution, x equals 2. When you plug in x equals 2 into this equation, it makes this parentheses a 0, which times whatever that is, it's going to be a 0. It's going to be a solution, so that works. Now this one. Let's maybe we'll be more careful this time and actually work it out. So you take the 8x plus 3, you set it equal to 0. Well, subtracting 3 on both sides looks like this. Dividing both sides by 8 looks like this. And so there's your other solution. So again, we got two solutions. If you like set form, you can do set form. Usually in set form, you put them in order. You put from smallest to biggest. So I put the negative 3/8 first because that's smaller than 2. So there's my set notation version of the answer. Just take a quick look at this, right? I got a negative 3/8. See how it's the 3 has to be divided by the 8? Because first you have to take the 3, move it to the other side of the equation, so the plus 3 becomes a minus 3, right? And then you have to divide by 8. Okay, so if you do those steps over and over, you start to just, basically you can look at the equation and read the answers right off it. So that's why I was saying that before. You can just read the answer. Once you've got it in perfect form, come on you. Once you've got it in perfect form like this, you can practically just read the answers. What would I have to put here? I'd have to put a 2. What would I have to put here? Well, you have to think a little bit. I'd have to put a negative 3 divided by 8. Yeah, that'll work. Okay. We should do some more of these, because different things can happen, you know. Like here, the right side is 0, the left side is not factored. Okay, do you remember something about the first kind of factoring to try is to pull out common factors? I see it, because they're both even numbers, I see 2's, and actually there's x's in both as well. So if you pull a 2x to the front, you're left with an x squared minus a, what now, a 49? Yeah, like that. Okay, cool. And then, do you remember that other thing about keeping your eye out for perfect squares? I suppose I could say, do you remember that other thing about factoring completely? Just keep factoring, keep factoring. So I saw x squared minus 49 as a difference of squares, so we get this pattern. And now look, it's nice and fully factored on the left, equals 0. So you look at all these factors. If I were to plug in a 0 right there, well, that would multiply and make the left side equal 0, so that works. That's a solution. If I were to plug a 7 right there, that would make my second parenthesis 0, which would make the whole left side 0, so that's a solution. And then here's another solution, negative 7. And so I've got 3 solutions here, negative 7, 0, and 7. That's supposed to be a 7. Let's make it look like a 7. That's better. Okay, cool. I'm going to throw a little PS on the side here. So you see this 2x cubed minus 98x equals 0. I see people do this a lot. They say, hey, you know what? I'm just going to cancel the 2. That's fine. That is completely fine. So you've got an x cubed minus a 98x. Excuse me. I used to know how to divide. I really did. Come on, you. Come on, you. It's come on in. Okay, so 98 divided by 2, that's going to be a 49x. Okay, cool. Go ahead. Yeah, that's fine. I mean, notice you can't set 2 equal to 0. It's not like losing the 2 is going to change your solutions or anything. So yeah, you can cancel the 2. But you're not going to cancel x's. No. You might say, well, why not? I'd have an x squared minus a 49, and I could get the difference of squares here, you know, da-dee-dee-dee-dee, everybody's happy, and nobody's happy, because you're missing a solution. Here you've got 7, here you've got negative 7, but wait, what about the solution x equals 0? You lost it. You lost it when you divided it. And by the way, you're not supposed to divide by 0 in the first place, right? So if you divide by x, and x is 0, you've just blown up the universe. You don't want to do that. I don't think you want to do that. No, you don't want to do that. No, because then you won't be able to do your math homework. Okay, so let's get this out of here. So anyway, that's just a no. Okay, so please never, come on, pen. Never cancel out, in quotes, a variable. You never divide by x, in other words. Don't do it. It risks division by 0. And I don't know if you've ever seen this, but there's an old trick that they show in some like high school math classes where they prove, hey, look, I'm going to prove that 2 equals 3. And they do a little algebra and you go, sheesh, how'd you get 2 equals 3? And the trick is there was a division by 0 in there. Because when you divide by 0, all hell breaks loose. Whoa, speaking of hell breaking loose. See? Divided by 0 and all that happened. Okay, so anyway, there's our answers right there. Now, one more example on this page. X squared plus 9 equals 0. Okay, it equals 0. That's good. It's not factored on the left. How are you supposed to factor that? Remember, we had a formula for a difference of squares. If you had x squared minus 9, you could say, hey, that's x minus 3, x plus 3. But this is a sum. This is x squared plus 9. Can you factor that? And back when we were doing factoring, lesson 40 said, I said, no, not yet, we can't. Because I had to wait until now to show it to you. It involves complex numbers. Notice it's a very similar, structure or whatever to doing a difference of squares. So if you had x squared minus 9, again, you'd say, hey, x minus 3, x plus 3. If you have x squared plus 9, you go x minus 3i, x plus 3i. You just add the I in there. First, let me prove to you that this actually works. If you FOIL this out, x times x is x squared. Notice you get a plus 3ix out here. Then you've got a minus 3ix right here. And then you've got minus 3i times minus 3i is negative 9i squared. Now the plus 3ix and the minus 3ix, those are equal and opposite, so those cancel out to 0. So you've got x squared minus 9, but remember I squared is the same as negative 1, so guess what? You really do have x squared plus 9. It works! In other words, your reward for getting to the end of page 1 is you now have a new formula, a new factoring formula. When you have a sum of two squares, it factors as a minus bi times a plus bi star. So, should we finish the problem? Yeah, we should finish the problem. So what we do then is we say, hey, I want to solve this polynomial equation. I'm going to do it by factoring. It's a sum of squares, and I know how to do that now. So the left side is x minus 3i, x plus 3i. This equals 0. And you'll notice that I either have to plug in a 3i here to make the left parentheses 0, or I have to plug in a negative 3i here to make the right parentheses 0. There are two solutions, and I'll just write them this way. Plus or minus 3i. Two solutions to that equation. Pretty slick, huh? This new formula? I can dig it, man. I can dig it. So, let's see. I'm going to give you a little observation here. See that equation? X was squared. We got two answers. See this equation? X was squared. We got two answers. See this equation? X was cubed. We got three answers. Whoa. X was squared. We got two answers. Okay, there's something called the degree rule that says, hey, x is to the fourth. I'm going to find four answers. That's the essence of the degree rule. Stated slightly more carefully, it says the degree of a polynomial equation, and that just means the biggest exponent on the x. So the highest exponent on x is called the degree of a polynomial equation. So the degree of a polynomial equation, hey, what'd you do? What'd you do? What did you do? Anyway, it tells you how many solutions you're hunting for. I want to be a little bit careful about what this means. We'll come back to that later. But it does tell you, it says how many solutions you're hunting for. So if I see a degree 4 polynomial, I'm hunting for 4 solutions. Ready? Let's go hunting. How are we going to find them? Well, your first idea might be, I guess I'll take the 4th root of both sides. So I'll try to take the 4th root of 16. Question mark? And the thing is here, if you take a course called Complex Analysis, it'll show you how to take the 4th root of 16. It's a really cool geometric construction, actually. But that's not this course. So how the heck are we going to find the 4th roots of 16? Well, let me phrase that differently. How are we going to find 4 solutions to this equation? We're going to do what we were doing on page 1. We're going to solve by factoring. So please don't be trying to take high order roots. Square roots are good. Square roots are safe. You know you're going to get 2 square roots because you put a plus or minus in front, right? Cube roots, fourth roots, fifth roots, sixth roots, all these higher roots, solve by factoring, please. So what's that mean? It means I need a 0 on the right. That's the first thing it means. So I subtract the 16 on both sides. Okay. Then you look at this thing and you say, what is that? It's two terms. What is that? Are they cubes? No. Are they squares? Yeah, those are squares. I have a difference of squares, right? This is x squared times itself minus 4 times itself. So it factors this way, x squared minus 4, x squared plus 4. We're factoring. We're factoring. Now make sure you factor all the way. Keep factoring. That's a difference of squares. So that breaks up further as an x minus 2x plus 2. That's a sum of squares, and we know how to do those now. X minus 2i. X plus 2i. Okay. Look at all that factoring, man. So, well, now I'm done factoring. Notice I'm going to have 4 solutions. X could be 2. If you put a 2 there, it makes that parentheses 0. If I put a negative 2 there, it'll make that parentheses 0. If I put a 2i right there, it'll make that parentheses 0. If I put a negative 2i there, it'll make that parentheses 0. Making any one of these parentheses equal to 0 counts as a solution, right? So I got 4 solutions. So I think the way I'm usually going to, you could use set notation, but to me it's easier to just say plus or minus 2 are both solutions. Plus or minus 2i are both solutions. 4 solutions total. Solve by factoring. It's just the thing. Let's look at this one. So again, thinking of that degree rule, I'm seeing degree 3 here. That means I should be hunting for 3 solutions. Trying to take 3 cube roots of 27, that's hard. I don't know how you would do that without knowing the special geometric construction thing. So we're in algebra. We can do it by factoring. So again, you're going to subtract 27 on both sides because you want to have an equals 0, right? This only works if if you have a 0 on the right? Hey, these things multiply to 0. Well, one of them must be 0. If this was a 5, you wouldn't say one of them has to be 5. That doesn't make sense. Maybe one of them's 2.5. Maybe one of them, it doesn't make sense. Anyway, whoa. We need a 0 on the right, is what I'm saying. Okay, now we need a factored form on the left. Hey, recognize that? That's a special pattern. That's one of our patterns. That's the pattern that says a difference of 2 cubes. Let me write the formula down. You should keep this formula handy because you're going to be needing it like all term long, pretty much. So if you have an a cubed minus a b cubed, it factors as an a minus a b times an a squared plus an ab plus a b squared. Okay, cool. What have we got? We've got an x cubed minus 27. So the a corresponds to the x, and the b corresponds to what times itself, right? So this is a 3 times a 3 times a 3. So the b is a 3. The b is a 3. The b is a 3. So how does this factor then? It factors as x minus 3. So I'm reading over here. Take the x and square it, plus take the 3 times the x, plus take the 3 and square it, 9. There's our factored form. Okay, time to try to read off solutions. Well, x equals 3. That's one of our solutions, because if I put a 3 there, it'll make that parentheses 0. Okay, now is the part where it gets a little bit more hairy. We need to set this to 0, right? Because if that parentheses equals 0, we get solutions too. Now, the problem is that part doesn't factor. X squared plus 3x plus 9, it doesn't factor. If it did, we'd have a different factoring formula, right? But we don't. So let me kind of pull over here. We want to take this x squared plus this 3x plus this 9 and set it equal to 0. But we can't factor it. What are you going to do? Tell me if you recognize this. Negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 9. I should really use parentheses. All over 2 times 1. Quadratic formula. It's a quadratic, right? So that's quadratic formula to the rescue. So I can find my solutions here. So it's a negative 3 plus or minus, and here I've got a 9 minus a 4 times 9 is 36. This is all over 2. So it's getting a little cramped here, but 3 plus or minus 9 take away 36 is a minus 27. That's all over 2. Okay, we're going to get these solutions. Really, we are. So negative 3 plus or minus. Now, since it's a negative, I can just put an I out front. Just doing one thing at a time here. Negative 3 plus or minus. Now, remember the 27. In order to simplify that, you want to try to think of a square factor. 9. Yeah, 9. 9 works. So you think of the 27 as a 9 times 3, because then you can take the square root of 9, which will give you a 3 out front, put it in front of the I, leave the other 3 inside, all over 2. And there's 2 more solutions, right? So this and this make our 2 solutions. Now, I'm going to need to cut this and make it smaller. Shrink. Oh, what'd you do? Tell you what, let's shrink the whole darn thing. Shrink-a-dink. What? Okay, I shouldn't have this much trouble. Come on, you. Shrink. I said shrink. That's pretty shrunk. Okay, that's shrunk. Love this. You might want to get yourself a tablet someday. It makes homework so much easier. It's like, oh, I ran out of room. Shrink it. No, I'm good. So anyway, what I was trying to do is I was trying to say this is a solution, this is 2 more solutions. So if you sort of join them together, you got 3 solutions to your degree 3 equation. Cool, right? All right. Let's do maybe another one on this page. Let's hope it fits. All right. What's the degree of this equation? The highest exponent is 5. This is degree 5. How many solutions are we hunting for? We're hunting for 5 solutions. 5. Woofda. Okay, first of all, what's this equals 3 stuff? It's supposed to say equals 0, so I'm going to try to make sure this all fits. So I got my x to the 5th, I got my 3x cubed, I got my minus x squared, and I'm going to subtract 3 on both sides because you have to have it equal 0. Now the left side you have to factor. 4 terms. Remember that whole factor by grouping thing? So looking at the first 2 terms, and I'm saying, hey, I can pull out x cubed, which leaves me an x squared plus a 3. Cool beans. Now I've got a minus, and it looks like there's nothing to pull out, but I always say pull out a minus 1. And then you'll have an x squared plus 3 over here too, because remember now, this negative 1 has to multiply the positive 3 to make a negative 3, right? You always got to remember that sign switcheroo thing. Anyway, next step in the factoring is to recognize that, hey, I got the same factor in both terms. So first I'm just going to pretend it ain't there. I got x cubed minus 1, but I got to put it back because it really is there. There we go. So when you factor by grouping, and we saw this a couple lessons ago, I guess, you end up with this. And wait a second, you're supposed to keep factoring, right? Factor, factor, factor. Now this isn't going to factor any further. It's a square, but 3 is not a square. Oh, so okay, we'll just have to leave that one alone for now. Yep. But this one we can do because it's one of those sums. It's one of those differences of cubes again. So I got the difference of cube factoring formula up there for your reference. Let me just try to do this. Instead of using the formula, let me do it by the do-si-do method. That's an x, x, x. That's a 1 times 1 times 1, right? So you take your x and your minus 1. That's how you get started. I don't know if that's a do-si-do or not. But anyway, that's how you get started, just like you were doing a difference of squares. It's a difference of cubes. So you start with the x minus 1. Now what you do is you take this and square it. Then you take these 2 things and multiply them together, 1x. And then you take this and square it, 1. See what I mean? Square this sucker, multiply them together, square this sucker. Do-si-do, yeah, boogie, 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 boogie. Something like that. Something like that. Anyway, so I factored that. However you get it, right? So I factored that into those two pieces. Now don't forget I still got this x squared plus 3 over here equals 0. Okay, and then again, this won't factor any further, and this won't factor any further. So we are fully factored. So it's a matter of lifting this up. Okay. So it's a matter of looking at these three parentheses separately. Now this one's good. All you got to do is plug a 1 in there. That's a solution. But this one, we're going to have to pull aside, and we're going to have to set to 0. I'll call this A. And then this one, we're going to have to pull aside, set to 0, and I'll call this B. Okay. So coming over here, A, I got to set this thing to 0. X squared plus x plus 1 equals 0. That's a quadratic formula thing. X equals negative b, b is 1. Plus or minus the square root, b squared, which is 1 squared, minus 4, ac, all over 2a. Okay, which simplifies. Negative 1 plus or minus square root of. Now notice up here, this is basically 1 take away 4. So that's a negative 3. So you know what? It's a negative 3. It's the square root of negative 3. That's going to be I square roots of 3 all over 2. And that's 2 more solutions. Okay, now I'm going to set it to 0b. So we've got to take x squared plus 3 and set it equal to 0. Now remember, it doesn't factor any further. So what the heck are you going to do here? Well, here's what you can do. Remember, well, maybe you don't remember because I haven't said it yet. So anyway, x squared plus 3 equals 0. Here's what you can do. You can subtract 3 on both sides. You can take the square root of both sides. So actually, I was saying it's safe to take square roots. It's not safe to take cube roots, fourth roots, fifth roots, or anything. But it is safe to take square roots of both sides. If you take the square root, you have to say plus or minus the square root of negative 3, which just means plus or minus I square root of 3. And there's 2 more solutions. So count the solutions. 1, 2, 3, 4, 5. It was degree 5. We found 5 solutions. Ain't that something? Ain't that something? So again, I need to shrink this up a little bit here. When I wrote on the paper with my... Why does it always unshrink? Somebody solve this problem for me. What are you doing? Do not. No, I'm trying to pinch you. Okay, stop. Whew. Okay. Okay, what was I saying? There. Oh, I know what I'm saying. I'm saying that this little trick I just pulled here, I got a name for that. It's called the square root method. In other words, if you have x squared, it might be easier just to put the stuff on the other side and just take the square root of both sides. Like here, this example is actually quite similar. Because we've got this x squared plus 32, and you couldn't call it a sum of squares, so you're not going to be able to factor it. If you can't factor it, then subtract 32 on both sides and take the square root of both sides. Plus or minus square root of negative 32. So that means plus or minus I square roots of 32. And then remember, you want to take the 32, you want to try to take out a square rootable factor. 4 is a square rootable factor, but think big. 16, that's better. So 16 times 2, which means in the end, when you take the square root of 16, you get a 4. So put the 4 in front of the I. That other 2 is stuck forever inside the radical. There you go, 2 solutions. By the way, degree 2, 2 solutions. Perfect, right? Here's one. This one's kind of groovy. Because if you recognize this, you can save yourself a little bit of effort. What I see most people do when they see this equation here is they say, well, that's not a factored form. And it ain't, you know, it's a plus. It's not a factored form. That's a sum. So what you could do is you could FOIL this out and recombine terms, and then you'll have a trinomial, and then you'll have to factor the trinomial, and then you'll have a factored form. But you don't have to. That's the only place x shows up. It's in that bubble. Notice the bubble's squared. That's the only place x shows up. And so up here it says a shortcut to consider if x is contained within only a squared object. It is here. This is the only place x shows up, and that's a squared object. So what we're going to do then, what I'm going to do, is I'm going to subtract 7 on both sides. Because look, I can take the square root of both sides right now. If I take the square root of both sides, the left side, all you do is lose the square. And on the right side, you'll have a plus or minus. And the square root of negative 7, which is basically I roots of 7. See, now that's not bad. Because now it's solving the way you usually solve these things. You just get x by itself, right? This is called a standard linear equation. So I'm going to add 4 to both sides. Now, rather than add 4 out here, which is kind of weird looking, we usually tuck the 4 in front like that. Okay, you can add 4 anywhere you want. Put it in front, that's a little more readable. And then notice we have to divide by 3. And so what we're getting is that x is equal to 4 plus or minus I radical 7 all over 3, which is kind of like engineering form, I think is what I called it in the last lecture. If you want the Alex form, if you're working on Alex, it's going to want you to break this up into 2 separate solutions. It's going to say 4/3. In fact, let me do this a little bit better. 4/3 plus, and this I root 7 over 3, I would actually write it this way, put the I separate out like this, and then 4/3 minus that thing. That's the Alex version of this answer. You can use either. I don't care which one you use. This one's fine. The engineering form's fine. Okay. So before we call it a day, I need to talk about the degree rule just a little bit more. So far, the degree rule seems to be working. I had degree 2. I got 2 solutions. I had degree 2. I got 2 solutions. I had degree 5, and I got 5 solutions. Seems to be working, right? So what's this comment up here about be careful what this means? Show you what it means. So right here, our last example. It's degree 3, right? We should go looking for 3 solutions. Okay, let's go looking. Now, the first thing to do before you start trying to unfoil is you say, wait a minute, let me look for common factors. Notice I got 4 everywhere, and I also have x everywhere. So I'm going to pull out the 4x, undistribute, so to speak. So if you divide the 4x cubed by a 4x, you're left with x squared. Here you're left with a 4x, and then here you'd be left with a 4. Okay, cool. So don't lose the 4x. It's part of your factorization. This trinomial here, well, we're going to assume that somebody multiplied 2 binomials. Now the x squared has to break up as an x times x, and then the 4, it's either 1 times 4 or 2 times 2, and it really looks like this is how it's going to work, because you've got a minus 2x, and a minus 2x gives me a minus 4x. And you've also got the minus 2 times the minus 2 gives me a plus 4, so it works. There it is. So now when you start reading off solutions, you say, well, I could plug a 0 right there. That would make the entire left side of the equation equal to 0. I could plug a 2 right here. That would make this parentheses equal to 0, which would then make the entire left side of the equation equal 0. So that's a solution. And then, well, a 2 there would also work, right? So notice we've got 2 solutions. What happened? What went wrong? We were looking for 3 solutions. We only found 2. Or at least we only found 2 different solutions. We still kind of got 3 solutions in a sense, right? I mean, 1, 2, 3. It's just that these happen to be the same, so you don't really want to count them twice, do you? And I'm going to say, no, not really. So, that's kind of what this is saying when it says some solutions can count twice, so to speak. Some solutions can count 3 times if you had x minus 2, x minus 2, x minus 2. But when you get this like a double solution, whatever you call it, just a little foreshadowing, so that just a little foreshadowing. Just a little foreshadowing. Okay, this is an idea called multiplicity. X equals 2 is a solution with multiplicity 2. And that's going to be an important concept when we start graphing polynomial graphs, things that are wiggly. If you know that x equals 2 has a multiplicity of 2, it actually tells you something about the graph. And we can save that for later. I just wanted to plant a little thing in your brain there. Multiplicity, it's coming. But we don't need it for this homework. So, okay, cool. Well, I hope that felt good. That was like a little workout, right? So now we can solve all kinds of, if it's a polynomial equation, factoring works really, really well. Don't forget your degree rule. I've got to learn how to